Today's topic is time varying electric field. Consider the uniform magnetic field B vector along with electric field E, which is uniform in space and varying with time. We consider uniform magnetic field B vector, and along with this magnetic field B vector we have electric field E vector, which is uniform in space and varying with time. Let E vector is along the direction of x-axis and varies sinusoidally with time t. Let E vector be such that it is given by E vector equal to E0 e to the power I omega t x cap. X cap shows its direction, which is along the x-axis, and it is time varying, and variation of time with t is given by this factor e to the power I omega t. That is, it varies with time t sinusoidally. E0 is its magnitude. If we write E0 e to the power I omega t by Ex and a symbol of AC above it, then we write E vector equal to Ex x cap. Here Ex is time dependent and it is E0 e to the power I omega t. Ex dot, it is the differentiation of Ex with time, now will be equal to I omega Ex. Ex is E0 e to the power I omega t. If we differentiate it with time t, we get I omega Ex. Equation of motion of charged particle under the action of Lorentz force can be written as m dv upon dt equal to q into E plus v cross b. Left hand side is mass into acceleration. Acceleration is written as dv upon dt, and it is the force. And this force is equal to force due to electric field and magnetic field. Force due to electric field is QE and force due to magnetic field is QV cross B. We can write this equation as dividing by mu to both the sides. We get expression for dv upon dt. dv upon dt is v dot, that is acceleration, and it is q upon m E vector plus v cross b. We write this as equation 1. Consider the uniform magnetic field B vector along the direction of z axis. So we can write B vector as B k cap. Let E vector is along the direction of x-axis and varies E vector is along the direction of x-axis and varies sinusoidally with time t. Then we have E vector equal to E0 e to the power I omega t x cap, and we write it as Ex x cap. We can write I cap in place of x cap, that represent a unit vector along the direction of x-axis. Then Ex dot will become equal to I omega Ex. Ex dot is differentiation of Ex with respect to time t. From equation 1, this is equation 1, dv upon dt equal to q upon m E plus v cross b. We can write this equation in its components. X component of this equation will be dvx upon dt equal to q upon m ex plus qb upon m vy. X component of v vector E vector is this Ex, because E vector is Ex x cap. So X component is Ex for E vector, and for V cross B, X, Y and Z components can be determined by solving the determinant. V cross B, value of V cross B can be determined by solving this determinant. V cross B is equal to this determinant. Components of V vector are Vx, Vy, Vz, and component of B vector are 0, 0, B. B vector is along Z axis, so only Z component is here, that is B. And by solving this V cross B, it is equal to I B Vy minus J B Vx, and Z component is 0. So X component of V cross B is B Vy, and Y component is minus B Vx, and Z component is 0. So we can write these three equations from this equation 1. It's X, Y and Z components. There are three equations for three components: X component, Y component and Z component. For X component, we have dvx upon dt equal to q by m ex plus qb upon m vy, and we write it as vx dot. Vx dot is dvx upon dt, differentiation of vx with respect to t. Similarly, we can write for dvy upon dt, and it comes equal to minus qb upon m vx, and we write it as vy dot. Similarly, dvz upon dt is 0, and we write it as equal to vz dot. So we have three equations for vx dot, vy dot and vz dot, that are dvx upon dt, dvy upon dt and dvz upon dt. These three equations are written as equation 4, 5, 6. From equation 4 we have equation 4 is for Vx dot. We differentiate it with respect to t. So we get Vx double dot, and differentiation of this equation 4 with respect to t will give q upon m ex dot plus qb upon m vy dot. Here we can put the value of vy dot from the next equation, which is for vy dot. Put value of vy dot from next equation, and ex dot is this equal to I omega ex. Put the value of ex dot from here, that is equal to I omega ex. So Vx double dot now becomes q upon m I omega Ex. Here we have substitute value for Ex dot, that is I omega Ex, plus QB upon M, and we put the value of Vy dot from this equation. Value of Vy dot is minus QB upon M Vx. So it becomes Q upon M I omega Ex minus QB upon M square Vx. In the second term, we have the quantity Q by QB upon M. And in the first term, we have only Q upon M. So we make this Q upon M as QB upon M. So we multiply by B and divide by B. So that the first term now become QB upon M I omega Ex upon B, and then minus QB upon M whole square Vx. This term QB upon M is cyclotron frequency omega c. QB upon M is plus minus omega c. So we write the value of QB upon M, that is plus minus omega c, and we get this Vx double dot equal to plus minus omega c I omega Ex upon B minus omega c square Vx. Take omega c square common. Minus omega c square common. So from second term we have Vx, and from first term we will get minus plus I omega upon omega c Ex upon B by taking minus omega c square common. Similarly, we can get expression for Vy double dot by differentiating this equation, which is for Vy dot. Differentiating it with respect to time t, we get Vy double dot equal to minus QB upon M Vx dot, and put the value of Vx dot from this equation. From this equation, Vx dot is equal to Q upon M Ex plus QB upon M Vy. Put the value of Vx dot here. We get Vy double dot equal to minus QB upon M Vx dot, and it is equal to minus QB upon M, and Vx dot is Q upon M Ex plus QB upon M Vy. In right hand side, inside the bracket, the first term contains Q upon M. We again make it as QB upon M, multiply by B and divide by B, so that inside the bracket we have QB upon M Ex upon B plus QB upon M By. Take QB upon M inside the bracket as common. Now we have this equal to minus QB upon M square into Ex upon B plus Vy, and QB upon M square is omega c square. Omega c is plus minus QB upon M. So we can write it as equal to minus omega c square Ex upon B plus Vy. Now we have two expressions, one for Vx double dot, and Vx double dot is this minus omega c square into Vx minus plus I omega upon omega c Ex upon B. We write it as equation 7, and expression for Vy double dot is given by minus omega c square Ex upon B Vy. We write it as equation 8. Now let us define Vp and a symbol above it as equal to plus minus I omega upon omega c Ex upon B. this term appears in this equation 7, I omega upon omega c Ex upon B along with Vx. So we define this second term along with Vx, negative of this second term. This second term is minus plus I omega upon omega c Ex upon B. So this second term, negative of this second term, will be equal to plus minus I omega upon omega c Ex upon B, and we write this negative of second term as Vp. Vp is plus minus I omega upon omega c Ex upon B. So that in this equation we have minus omega c square into Vx minus Vp. Similarly, in this next equation, we have inside the bracket as Vy plus Ex upon B, and write this term with Vy, that is Ex upon B, and negative of this term we write it as Ve. So we define Ve as minus Ex upon B, and inside the bracket then we have it is equal to Vy minus Ve. Now these equations 7 and 8 becomes as Vx double dot equal to minus omega c square Vx minus Vp, and Vy double dot is equal to minus omega c square Vy minus Ve. We now try for a solution which is sum of a drift and a gyratory motion. We now look for solution of these two equations. Equation first is for Vx. We have the terms Vx and Vx double dot. In next equation, that is for Vy, we have terms for Vy and Vy double dot. And we try for such kind of solution. Vx equal to Vp plus V perpendicular e to the power I omega ct. V perpendicular e to the power I omega ct is a solution of simple harmonic motion. So we try for such a solution. Vx minus Vp, that quantity is inside the bracket in equations in this equation, that is Vx minus Vp, and we write Vx minus Vp as V perpendicular e to the power I omega ct. We look for a solution, we try for a solution such that the quantity inside the bracket Vx minus Vp, we assume like this equation is simple harmonic motion in Vx minus Vp, though it is not true, but we are trying for such a solution. Then Vx minus Vp, if it is a solution of simple harmonic motion, then Vx minus Vp is V perpendicular e to the power I omega ct. So that we can write Vx equal to Vp plus V perpendicular e to the power I omega ct. Similarly, we try for solution for next equation, that is for Vy and Vy double dot, and try for such a solution, that is Vy equal to Ve plus minus I B perpendicular e to the power I omega ct. Here plus minus I sign is extra. We can avoid this plus minus I, or this sign may be introduced for some phase change between Vx and Vy. Plus minus I sign represent phase change of pi by 2. So we look for such a solution that the quantity inside the bracket in this next equation is Vy minus Ve, and we look for Vy minus Ve as equal to V perpendicular e to the power I omega ct, plus minus I sign is also introduced, and then Vy equal to Ve plus minus I V perpendicular e to the power I omega ct. Differentiating twice with respect to time, we get, if these equations we differentiate two times, differentiation of Vx will give Vx double dot by differentiating two times with respect to t. Then it comes differentiation of Vp will give minus omega square Vp, because Vp have term like e to the power I omega t. So two times of differentiation will give minus omega square, and differentiation of Vp with two times with time t, we get minus omega square Vp, and the second term, if it is differentiated two times, it will give minus omega c square V perpendicular e to the power I omega ct. And V perpendicular e to the power I omega ct from this equation is equal to Vx minus Vp. From this equation, that is equation 13, we put the value of V perpendicular e to the power I omega ct as Vx minus Vp here, so that this becomes equal to minus omega square Vp minus omega c square into Vx minus Vp. Now we can write this equation as minus omega c square Vx. First we write term of Vx, then we write terms of Vp, and with Vp we have omega c square minus omega square. Similarly, we can write for Vy double dot, differentiating this equation for Vy with respect to t two times, and get Vy double dot equal to minus omega square Ve. Ve also have time dependence as e to the power I omega t. So two times differentiation with t gives minus omega square. So Vy double dot is equal to minus omega square Ve minus omega c square plus minus I V perpendicular e to the power I omega ct. Differentiation of second term gives minus omega c square extra. And this quantity inside the bracket, that is plus minus I V perpendicular e to the power I omega ct, value of this we can write from here, from this equation 14, plus minus I V perpendicular e to the power I omega ct is Vy minus V. We put the value of this term here and get this expression minus omega square V e minus omega c square Vy minus V, and we can write it as minus omega c square Vy plus omega c square minus omega square V. We write the terms of Vy and V separately. So we see that in these two solutions, if we write similar solutions, if we can omit this term plus minus I in second equation, we can choose similar solutions as Vx equal to Vp plus V perpendicular e to the power I omega ct, and in second solution we can choose similarly as previous solution, Vy equal to Ve and omit plus minus I, and we can write simply plus V perpendicular e to the power I omega ct. Then also we have these similar expression for Vx double dot and Vy double dot. Now we assume these two solutions Vx and Vy for these two equations which are for Vx double dot and Vy double dot, and get expressions for Vx double dot and Vy double dot as these two equations. Now we compare these two equations for Vx double dot and Vy double dot. These are equations 11 and 12, and we now have these two another equations for Vx double dot and Vy double dot, and these are equations 15 and 16. If we compare these equations, in first one we have Vx double dot equal to minus omega c square Vx minus Vp, and here we have Vx double dot equal to minus omega c square Vx plus omega c square minus omega square Vp. These two equations will be same only if we assume that omega square is much less than omega c square. When this condition is satisfied, omega square is much less than omega c square, or we can neglect this omega square term both in both of these two equations 15 and 16. If we neglect the term of omega square, we find these two equations as equal to these two equations for Vx double dot and Vy double dot. So if we assume this solution Vx and Vy, this is true only when omega square is much less than omega c square. So if we make the assumption that E vector varies slowly, omega appears in E vector. E vector is contains the term e to the power I omega t. So omega appears in E vector, and if we assume that E vector varies slowly so that omega square is much less than omega c square, frequency of variation of E vector is much smaller such that omega square is much less than omega c square, then equations 13 and 14 are approximate solutions of equations 11 and 12. Equation 13 and 14 tells us that the guiding center motion has two components. The y component perpendicular to E vector and B vector is usual E cross B drift, except that Ve now oscillates slowly at the frequency omega. The x component, a new drift along the direction of E vector, is called the polarization drift. These are the two drifts. Ve, it is the drift due to electric field, and it is equal to minus Ex upon B. It is the drift due to electric field, Ex. and the second is Vp, which is plus minus I omega upon omega c Ex upon B. We call this Vp as polarization drift. The X component, a new drift along the direction of E vector, is called the polarization drift by replacing I omega by delta upon delta t. We can generalize equation 9 and define the polarization drift as Vp equal to plus minus 1 upon omega c B delta E upon delta t. Delta upon delta t, if we differentiate E vector, it gives I omega. So we replace I omega by delta upon delta t in this expression for Vp, that is polarization drift. Replace I omega by delta upon delta t and we get Vp as equal to plus minus 1 upon omega c B delta E upon delta t. Polarization drift for ions and electrons are, we write this polarization drift Vp. For ion we write it as Vip. Ion is positively charged particle. Here we put the value of omega c. Value of omega c is Qb upon m. For Q we write as E. E is the charge on ion, positive charge. So for omega c we write Eb upon m, and for m we write capital M, that is mass of ion. Similarly, for electron we write this polarization drift as Vep. Here also we put the value of omega c equal to minus Eb upon m, because charge of electron is minus E. And for mass we write small m, that is mass of electron. So this polarization drift Vp, for ion we write as Vip, and it is equal to m upon Eb square delta E upon delta t by putting the value of omega c equal to Eb upon capital M. Similarly, for electrons we have Vep as equal to minus m upon Eb square delta E upon delta t. It is obtained by putting the value of omega c as minus Eb upon small m. Since Vp vector is in opposite direction for ions and electrons, there is polarization current. Now current density J is defined as NeV. N is number of charged particles per unit volume, E is charge on each particle, and V is its velocity. So for ions we have current density as NeVip, and for electrons we have NeVep with minus sign. So polarization current density Jp vector can be written as NeVip minus Vep. Velocities, drift velocities for ions and electrons are in opposite direction, so we have this negative sign. It is equal to, by putting the value of Vip, that is m upon Eb square delta E upon delta t, and Vep is minus m upon Eb square delta E upon delta t. If we put these two values here, polarization current density Jp vector now becomes Ne upon Eb square capital M plus small m delta E upon delta t. Small e is cancelled out and we get it equal to n into m plus small m upon B square delta E upon delta t, and we write small n into capital M plus small m as equal to rho. Rho is charge density, charge per unit volume. Rho here is not the charge density, it is simply density, mass density. It is mass per unit volume. Rho we write for n into capital M plus small m. N is number of particles per unit volume, and capital M plus small m, this is mass of electron ion pair. So small n into capital M plus m represent mass per unit volume, that we write as rho, simply density, not the charge density. So Jp vector, polarization current density, now comes equal to rho upon p square delta E upon delta T. This figure shows the polarization drift, Vp. The physical region for the polarization current is shown in this figure. Consider an ion at rest in a magnetic field B vector. Ion is represented by this positive sign because it is positively charged particle, and let it is at rest in constant magnetic field. Direction of magnetic field is shown here by dot. It means it is perpendicular inside to the page. If positively charged particle, that is ion, is at rest in magnetic field and electric field is E is applied. If an electric field E vector is suddenly applied, ion begin to move in the direction of E vector. There will be force Q E vector in the direction of E vector because it is positive charge particle. So if ion is initially at rest and magnetic field B vector, ion is at rest in the presence of magnetic field, there will be no force because force due to magnetic field will be Q V cross B and it depend on velocity V. If velocity is 0, force is 0. But suddenly electric field is applied, it begins to move in the direction of E vector. So when E vector is suddenly applied, ion begin to move in the direction of E vector. As soon as ion acquire velocity V, it feels a Lorentz force, that is force due to magnetic field, equal to E V cross B, and begin to move downward. So this positively charged particle is initially at rest in the presence of magnetic field B. Magnetic field is perpendicular inside to this paper and electric field E is applied suddenly in the direction as shown in this figure. Then it begins to move in the direction of E vector, and when it acquires some velocity V, then the force due to magnetic field is applied on it and it is E V cross B. So it begins to move in downward direction. If E vector is now kept constant, there is no further Vp drift but only a Ve. However, if E vector is reversed, direction of E vector is opposite, there is again a momentary drift, this time to the left. If direction of E vector is reversed, now this momentary drift will be along left side, opposite direction. Thus Vp is startup drift due to inertia and occurs only in the first half cycle of each gyration, during which E vector changes. Consequently, Vp vector goes to 0 with omega upon omega c. Vp depend upon omega c. If omega upon omega c tends to 0, Vp also tends to 0.